Yeah, so as Ruth said in my introduction, which I really appreciate, I right before this, I did my PhD at Georgia Tech, and I worked on robot learning from humans. So thinking about how robotic agents could extract information from human teachers. And then my postdoc, I really focused more on multi-agent learning. And so starting to think about communication. And this is actually work that I'm presenting from work done for my postdoc at the time, Facebook AI Research, now Meta AI. And currently I'm a research scientist at DeepMind. And so I'm starting to kind of expand the set of problems that I'm thinking about as well. Today I'm going to discuss the work from my postdoc on zero-shot emergent communication. And as I hope to continue building upon some of these ideas, I'm keen to share with you guys the exciting progress we've made and discuss thoughts and feedback you may have. So why cooperative multi-agent systems, which I probably don't have to really motivate this audience, but the world is inherently multi-agent, you know, when you think about biological systems. And my belief and kind of underlying motivation for this work is that communication and coordination amongst AI agents and humans are necessary for coexistence between human AI agents. And, you know, as technology becoming more ubiquitous, like the self-driving car, or like robots in factories, or human robot interaction, which is what I thought about in my PhD, we really want to try to create algorithms and methods that can enable this seamless coordination and communication, both with other artificial agents as well as human agents. And so I think there are a lot of relevant application domains. In particular, these are some of the ones that I think are interesting, but also that I think are really nice and for modeling multi-agent systems. But these are kind of two of the ones that I'm going to be using as a high-level motivation. The work that I'll talk about is going to be more abstract and you know, it's more thinking about some fundamental questions, but it's motivated by these kind of application domains where you might want to see communication protocols. So imagine that you have all of these embodied agents operating in a shared environment. So, you know, like these cars, for example, and there's also human agents. And so, you know, what if you wanted them to learn to communicate in order to aid in coordination, which is a reasonable goal given an autonomous vehicle ecosystem. So you might say, well, what about using something like supervised learning from data sets or imitation learning from demonstrations? And while these are promising methods, they require huge existing data sets. Supervised learning requires huge existing data sets for each embodied agent. So for each type of car embodiment, you'd need that. And then and imitation learning also would require you know, a high cost in terms of human time in order to give demonstrations. But multi-agent reinforcement learning provides an opportunity to allow agents to learn a protocol solely through agent-agent interactions. So we can turn compute into data. And so one question that follows from this is, even though using multi-agent RL is a powerful mechanism, a key consideration is in learning protocols that will generalize to unseen partners. So what we would not want is that for every agent, they have to train with every other potential partner in order to infer a general communication protocol. What we want to see is that agents can generalize even though they only have a limited number of training partners. These are the collaborators from this work. And at the time we were all at Facebook AI Research, although some of us are now at different places. And the papers below are the ones that I'm referencing. So the motivating research question here is, how can general communication skills emerge in embodied agents? And here I say through physical action. So meaning that not necessarily through language, but through some type of action space that the embodied agents might have. And it's motivated by the idea that these agents inherently communicate through movement, and to move towards human level embodied intelligence, we need to enable artificial embodied agents to communicate through this more realistic channel. So first, I want to give some background on learning communication protocols and the multi-agent reinforcement learning formalism that we use. So in learning a communication protocol, let's say you have a population of agents. Here's a blue, a green, and an orange, and a set of communicative goals. The underlying idea is that each agent in the population must learn to generate messages for every communicative goal in the library. And so the learning problem is for every agent to learn a policy mapping the set of communicative goals to the message space, at least for the sender agents. So referential games are what we use to, or are commonly used, not, I shouldn't say what we use, they're other types of communication games, but referential games are commonly used for communication protocol learning, and they're based on multi-agent signal, the signaling game. So the premise of the game is as such. You have a sender agent that gets some kind of goal as input, a communicative goal. It has to generate a message for a receiver agent to observe, and then the receiver agent makes a prediction about what goal is being communicated. And then the loss is looking at the distance between the intended communicative goal, so the one that was referred to, and the predicted goal. So basically, the goal is for the receiver to infer what the sender was signaling or referring to. Two important assumptions typically persist for this problem setting. One is that typically it's a discrete communication channel, and the other is that it's typically a cheap talk setting, so that actions have no cost. And so this is a sample of prior work, a visual sample of prior work. So I'm actually not going to delve into this, and it's not meant to be exhaustive, but to briefly illustrate kind of where recent prior literature is focused. This is more in the deep learning age, which is why you see some depictions of neural network architectures. But the key limitation for embodied agents is the two assumptions that I just mentioned. And so in this particular talk, so we do have work that relaxes each one of these assumptions, but in this talk, I'm going to focus on the work that relaxes the assumption of cheap talk. So focusing on costly communication settings. Okay, so the problem formalism. So this is a fully cooperative problem setting. The assumption is that communicative goals are given a priori and that the protocol emerges solely through agent-agent interaction. So there's no data or supervisory signal, although that could be an interesting extension. This is formalized as a decentralized POM-DP. And so you have in some set of agents, you have a set of finite states, a set of joint observations, although agents can have private individual observations. Joint communicative, all actions are communicative actions in this model. And then there's a shared reward for all agents, importantly, a team reward. So with respect to the cooperative multi-agent reinforcement learning problem, a visual depiction of this is you have some learning agent I, and it is able to take its own observations, O sub I. You have another learning agent J that is effectively the environment that agent I is interacting with, and that environment seems non-stationary from the perspective of agent I because agent J is also learning at the same time, so its policy is changing. So over time, the environment seems to be changing. And there's some shared reward that the agents get. Each agent is able to take their own action, which will influence what the other agent sees. And so the goal is to maximize the total shared return per episode. And so this is going to be a centralized training regime where agents can share information and provide feedback to each other during training time, but decentralized execution at inference time. Agents can only use their own sensory input and learn models. So now I'm going to describe the problem setting, this zero-shot coordination problem setting, which is what we build upon for this zero-shot communication setting. So zero-shot coordination was introduced at in work at ICML 2020, which and the problem setting is defined as a setting where agents must coordinate at test time with other agents who have been independently trained. And so this problem setting in general, of course, is very related to the ad hoc teamwork problem setting. But we're going to build upon some of the concepts introduced in this work for the work that I'll discuss today. So it introduces equivalence mappings or symmetries of policies, which are bijective mappings of policies, and formalizes symmetries for each underlying element of the decentralized POM-DP. Okay, so we formalized the zero-shot communication problem setting, which you can see as an instance of the zero-shot coordination setting, where the coordination goal is to learn a communication protocol that effectively generalizes to unseen agents. And so the protocol for the zero-shot coordination setting more generally is to train in self-play and evaluate in cross-play. So here you have two different sets of agents that are training in self-play, a green pair and a blue pair. So I'll just go over the green pair. So the green pair is our pi1, which is our sender policy, and it'll take a communicative goal G and its own private observation O1, and it takes an action A, which is a communicative action, and then our receiver policy, Pi2, will take as input action A, and then it can make its own private observation O2. And then, of course, there's the shared reward. And so this is happening for both of these agents that are training in parallel, but are training independently of one another. And then at test time, in order to test zero-shot communication, what happens is that basically agents are swapped, partners are swapped. So every sender is paired with every receiver they did not see at training time. And what we want to assess is whether or not they're able to have communication success. So you might say this seems like a perfectly reasonable regime for training, and self-play has been quite effective in multi-agent reinforcement learning. So what's the problem with using self-play for training these zero-shot communication protocols? So the one challenge is that self-play has many equivalent but incompatible joint policies, and protocols are just joint policies, basically. And so successful coordination, so here's a simplified picture of an optimization landscape, and you can think of each of these dots as a globally optimal communication protocol or joint policy. So successful coordination means that the two agents agree on the same protocol, which means they converge on the same optimum. So now let's say that for illustrative purposes, this is a bit exaggerated, but let's say one of these communication protocols was English and one was German and one was French. And so if you have two different sender-receiver pairs training in parallel but independently of one another, there's no reason to believe a priori that that the two pairs of agents will converge on the same protocol, converge on the same optimum, because they're equally, they're equal, but they're equivalent, but they're incompatible. So so if you put that an English sender and a German receiver to talk to each other in the left picture, then the challenge is that that you would have communication failure because they didn't learn the same protocol. So what we want for zero-shot communication is to bias the optimization landscape in such a way where there's one global optimum. Or if there is more than one global optimum, then we have a way of learning a distribution of a global optimum. But in this case, what we see now is if you have these separate sender-receiver pairs training in parallel and independently, even though they didn't see each other at training time, what you might expect is they both converge on this global optimum, which may be the German communication protocol. And now when you put the German sender and the German receiver to talk to each other at test time, you would expect much higher communication success. So this is kind of the underlying idea, or the underlying intuition. So our general approach is to introduce bias into the protocol learning with priors on the solution space. And we want to use real world constraints for these. We don't want to just introduce arbitrary biases, but biases that are motivated by the types of problem settings that we're interested in. But what we'll see is that there are many situations where even after inducing bias, we're still going to have more than one global optimum. And in that case, we want to adapt our learning objective to be able to learn some distribution over equivalent global optima. So that would work whether there's one global optimum or several. And then we're going to exploit this idea of equivalence classes of communicative actions in order to do that. So for inducing biases, we want to take priors from the types of settings that embodied agents which were motivated by would come from. So there's a cost to physical energy exertion. If I wanted to like wave, then it would actually cost me an energy. And so what we consider this to be a costly communication setting or a non-cheap talk setting. We also want to do some distribution over our goals. And so we take this Zipfian distribution, which has been used in quantitative linguistics and also just in ecology. And it basically instantiates this principle of least effort. So assigning higher distributions or a higher probability to words or sentences that require less effort or that are more common. And so when we put these two together, this incentivizes a minimal effort protocol where what we'd expect to see is communicative goals that occur with higher frequency should be assigned less energy, should be mapped to less energy. So they're less costly. So you can imagine that like something like saying hi maybe occurs a lot more frequently than saying turn right. And so in that case, the saying hi would be assigned, it would be a communicative goal that would be assigned lower energy, but a higher probability of occurring. And so this incentivizes a minimal effort protocol where the communicative goals that occur with the least frequency should be, or with the highest frequency should be mapped to kind of the minimal effort actions. Okay, so I'm going to skip this slide. So that picture suggested that that there should be one global optimum given that you put these two priors together. But what about when we have symmetries in realistic communication? So now I have a communicative goal. I'm a car, and I'm trying to tell another car maybe to go ahead in the in the autonomous driving vehicles ecosystem. And so, or maybe I'm a person because I have waving. So, but let's say there are three different ways to do this. One way may be that I can wave to the car to say, come, go ahead, it's your turn with my left hand. Another way could be that I could wave with my right hand to say, go ahead, it's your turn. Another way could be that I nod my head to say, you go. So let's say that all three of these exert the same amount of energy. Then the challenge is that there are three different communication protocols that can instantiate the same communicative goal. And these are all equivalent minimal effort protocols, but they're incompatible. So now if I'm a sender agent who trained with if I'm a receiver agent who trained with a sender that waved its left hand to tell me to go ahead, but at test time, I face a sender agent that nods its head to tell me to go ahead, then we're going to have a communication failure because the communication protocols we learned are equivalent, but they're incompatible. So how does symmetry impact the optimization picture that I showed you before? If we have no symmetry, so there's no redundancy, because symmetry is effectively coming from equivalences or redundancies, right? So if there's no redundancies, every action has a distinct cost, every goal has a distinct likelihood, then you should actually have one unique minimal effort protocol, and then self-play is sufficient to train multiple pairs of sender-receiver pairs because they can all converge on the same globally optimal protocol. But if you have symmetries in this space, what this means is multimodality or symmetries in your action or goal space. So many actions have the same cost or many goals have the same likelihood. Then what you have is multimodality in the optimization landscape. So the original picture I showed you where different pairs of independently trained sender-receiver pairs are likely to converge on different optima. And so, okay. So we're going to focus on the action symmetry in this case, on action symmetries in this case. So, so here's a discrete domain that we use to make this a little bit more concrete. So the top row is depicting one sender receiver policy or joint policy, and the bottom row is another sender receiver joint policy. So let me tell you what each of the columns mean. So the first column on the left is going to be a visualization of the sender policy. So the vertical axis is the input for the sender, so the communicative goals it gets as input, and the horizontal axis is the output for the sender, so the actions that it can take as a result of those goals. In the middle column is the receiver policy. So the vertical axis for the receiver policy is the input for the receiver. So the the actions that it can observe that the sender took. And the horizontal axis for the receiver policy is the output for it. So the goals that it can predict given actions that it observes. And then the right column is basically confusion matrix, a visualization of the confusion matrix, which shows where sender and receiver agree. So what you want to see is probability mass along the diagonal, because that means that the true intent by the sender is equivalent to the predicted intent by the receiver. So a couple other things to note here is that for the sender policy, the lower the index of the goal, the higher likelihood it is. So the goal 0, which is at the bottom of the y-axis, occurs at the highest frequency. Goal 1 occurs at the next highest frequency, and so on and so forth. And then on the y-axis of the sender policy, the more to the left the action is, the lower cost it is. So action 0 has the lowest cost, and then you see there's these actual classes. So actions 1 through 4 all have an E1 means like energy 1. So they have an energy of 1, so they have the same amount of energy or cost, and then so on and so forth. So these are like energy classes to tell you how much cost or energy these actions require. So ideally what we want to see is that intent 0, which is the bottom intent, should be mapped to action 0, which exerts the least amount of energy. And that's the only action that will, kind of make this a minimal effort protocol. But for goals 1 through 4, they can be mapped through any of the actions 1 through 4. If you learn in self-play and still be a minimal effort protocol, because all actions 1 through 4 have the same amount of energy. So those goals can be mapped in any permutation, which is why the top joint policy and the bottom joint policy are equivalent, but they're incompatible. So in self-play, these agents do very well. You see most of the probability masses along the diagonal. However, when we go to evaluating cross-play, which is zero-shot coordination, so now we put the orange with the green and the green with the orange, what we see is that the agents do much worse. So like if you look at the confusion matrix on the very right side, the agents are able to get action 0 or intent 0 correct because basically it can only map for action 0 because that's the only action that uses the least amount of energy. But for intents 1 through 4, they're not able to agree upon which actions would instantiate those intents because they learn different communication protocols. And it turns out that action 0 or intent 0 occurs about 44% of the time. So basically it can't do better than just predicting the most likely action, or the most likely intent, I'm sorry. The receiver can't do much better than just predicting the most likely intent. So how do we address this gap in communication efficacy between training partners and novel partners? And so our method that we introduce here is quasi-equivalence discovery. So, so now I'm going to talk a bit about that. So the baseline is going to be training using self-play. So again, the same picture, but now the objective function. Self-play tries to incentivizes each sender and receiver to optimize for its training partner. So basically the receiver is optimizing for an individual sender. And it's maximizing kind of the objective between these two training partners. But again, we know the challenge is that when that happens, if you take a different set of sender-receiver pair that trains independently, they may converge on a different global optimum. So let's say they converge on the right global optimum, then the two will not have compatible communication protocols. So what we want to do is exploit this idea of equivalence mappings that was introduced in the paper on zero-shot coordination from ICML 2020, and they introduced this other play objective function, which basically modifies the self-play objective function such that the sender policy is learning to optimize for an equivalence class over receiver policies, or vice versa. The receiver policy can learn to optimize for an equivalence class over sender policies. But what this now means is that instead of maximizing over instead of just optimizing for your training partner, you're optimizing for your training partner plus some set of symmetry equivalent policies, any of which you might presumably face at test time. Okay, so what we do is we propose, So what we do is we're going to first do some analysis, some theoretical analysis to understand how the other play objective function will change our communication objective. And then I will talk about the actual method that we use that uses this objective function as part of its inner loop. So so the communication, so typically what you have for your communication objective in a referential game is just this communication efficacy part. So just log likelihood of the goal predicted, the goal that the receiver outputs given the goal that the sender inputted. So it's G given G. So what we want to see is that the receiver predicts the correct goal given that the sender was trying to communicate some goal. So what we add to this is we add the cost of the joint policy because we're working in a costly action regime. So we're looking at non-cheap talk settings. So now we have a cost. And then we also add this expectation over equivalence classes, which comes from the other play objective. So, so when we expand out, the green tells you what expands from the previous line. So when we expand out the previous line, what we're doing is saying we want to take some expectation. So we want to basically look at the probability of each, the log likelihood of each goal in the set of communicative goals, given the goal that the sender intended, times the prior on that goal. That's what the first term expands to mean. And then the second term says the cost of the action times some probability that action is taken by the sender, given the goal, and then some prior for that communicative goal. Okay, so then in the next line, then I'm also expanding out the expectation from the previous line, the expectation over equivalence classes. So now what you have is inside of the log, you have given any action, you have some product of the receiver policy of some goal it predicts given some equivalence class of the action, times the sender policy, the likelihood of the sender taking that action given the goal that it was trying to communicate. One challenge, however, is that you have this summation inside of the log likelihood. And so it becomes difficult to understand what is happening, what is being optimized for if we can't simplify this further. But we can use Jensen's inequality in order to pull that summation out. And so now what we have is just a product inside of the log. So we have the log likelihood of the receiver policy. So what we had initially is going to be greater than or equal to some, log likelihood of the receiver policy times the sender policy. And I just, on the right side, I just basically condensed that back to a smaller term, which says take some expectation of actions given being sampled from the joint policy and then the cost of that action. So this is nice because now we can expand this further. So we can basically take the probability on the outside from the previous line and then separate this product as the sum of the logs. So we can say that probability times the log of the receiver policy in the first term, and then plus that probability times the log of the sender policy in the second term. And so effectively, there's some lines in between in the derivation, but effectively what this tells us is that this objective function is trying to maximize mutual information between the set of goals and the equivalence classes on communicative actions. So that means that if I know the communicative goal, if I know the communicative goal if I know the goal that's being communicated with very high probability mass, I should be able to locate which actions in the space, or with very high confidence, I should be able to locate which actions in the space have high probability mass. So given I know the goal, I should be able to determine, or I should be able to predict which action should have high probability mass, meaning which action should be taken to communicate that goal. And given I know what action has been taken, I should be able with very high confidence to predict which goal was being communicated. So this is what maximizing for mutual information would give us. But now the question becomes how do we obtain these equivalence classes? Okay, so a key limitation in the prior work and the other play work is that it assumes these equivalence mappings are given, the symmetries are actually given. But this is a key limitation in practice. And so the algorithm that we introduced, quasi-equivalence discovery, is seeking to discover the equivalence mappings or the symmetries. So it's automatically discovering the symmetries through the multi-agent interactions. So we initialize some set of equivalence mappings with the identity mapping. And then for each iteration until convergence, there's training of the communication protocol. So we train some optimal set of zero-shot coordination or zero-shot communication joint policies, given the objective function that I just derived in the previous slide. And then in the next slide, we are going to extract in the next step, we extract new symmetries from those optimal policies. So I'm going to actually expand, I have a diagram to kind of show like how we do that. So there are two steps: protocol training and symmetry discovery. So in the protocol training, what we want to do is take as input some joint policy or some set of joint policies, pi 1 through pi n, and then some symmetries. And these symmetries are initialized the identity matrix initially, or just a set with the identity matrix initially, and we're going to be building upon these symmetries over time. And in this case, the joint policies are they consist of only a sender-receiver policy. So the second line just means that you only have pairs of sender receivers. And then the output of this protocol training step is some kind of optimal joint policies. So we would have ideally want to train a set of joint policies, and then we take some subset of those that we believe to be optimal. And so these policies are given, these optimal policies are given to the symmetry discovery step as input. The set of goals is given as input as part of the problem, and then as well as the symmetries from the previous step will also be given to the symmetry discovery step. And so the output here, so this is just kind of the overall picture. The output of the symmetry discovery step is to update the set of symmetries. So as a big picture thing, the protocol training is taking in the joint policies and the symmetries. It tries to learn optimal joint policies and pass those over to the symmetry discovery step. And the symmetry discovery step will then try to update the set of symmetries and then give that back to the protocol training. And so this will happen until some convergence. More specifically, what's happening inside of each step is that over some set of M training episodes and some set of case samples, there's a signaling game that is being played in the protocol training step using centralized training. It will output some performance for each of the joint policies and some cost for each of the joint policies and to the objective function, and then that objective function will be used to effectively update the policies. And this part in the square will actually happen over, like I said, over M episodes. So the objective function that I introduced will be used inside this protocol training step in order to train the optimal policies with the signaling game. And then over here in symmetry discovery, what we want to do for every single goal in the set of goals and for every single pair of agents, IJ, there's some, given that there's some goal, you take some pair of agents, sender policies, so pi1 sender policy and pi sub I sender policy and pi sub J sender policy. And given that they were trying to communicate the same goal, if they took two different actions, AI and AJ, what we can infer from this is that there's a symmetry between these two actions. These two actions were used to communicate the same goal. So it's important that these policies are optimal. So given that you've learned some optimal policies from the protocol training step, in the symmetry discovery step, what it's going to do is take those optimal policies and say, in particular for the sender policies, if you have two different senders that are communicating the same goal using different actions, we can infer that those actions are symmetric, they're equivalent. And so we can put them in the same equivalence class and infer a mapping between actions AI and AJ. And so you can, if it goes through every single communicative goal and every pair of agents, then it's going to be able to update the set of symmetries using all the times that two different agents took different actions to communicate the same goals, and then give that back to protocol training and so on and so forth. Okay, so so the two things that I want to talk about now with respect to this kind of overall framework that I just laid out is how the signaling game, give you an intuition for how the signaling game is played using these equivalence mappings, and then tell you how the mapping, this phi ij, is learned using different actions or equivalent actions taken from two different optimal policies. So first, I'm going to start with the actual mapping. How do we infer the mapping? And so what we do here is if you have two different, so let's say you have two different actions. Sorry. Let's say you have two different actions taken from two different optimal senders, and you want to learn a transformation between them, then we simply learn a transformation matrix. And so so we're trying to minimize the KL divergence between the transformation on action A sub J and action A sub I. Yeah, and the effect of that is as we learn this, we learn some transformation, and then we can put these, the implication is that these two are in some equivalence class. All right, so that was the first thing I just showed was like, how do we, or from that overall framework, how do we infer the mapping, the transformation? And now I'll say, what do we do with that mapping? So how do we play the signaling game given that we have the mapping? And there's just kind of the key parts of each of these steps. So the signaling game with symmetries. So a sender agent gets a goal as input. It takes an action. That action is multiplied by a transformation matrix, so it's passed through a transformation. And then a new action, when you do the transformation, a new action AI is outputted. So the receiver sees AI, even though the sender took AJ, because we transformed AJ to AI. And then if the receiver makes the correct goal prediction, what we can infer from that is the sender now learns that it can take action AJ to communicate goal G, and the receiver learns it can, that if it sees action AI, that means goal G. Okay, so now how do they both end up learning that the other action was also appropriate? So in this game, the sender takes AJ and the receiver sees AI. So later, we reverse the relationship where the sender takes AI and the receiver sees AJ. So this is a different transformation matrix. It's phi ji instead of phi ij. So it's a different transformation matrix. But again, we do this transformation. The sender takes AI. The receiver sees AJ, and then the sender updates its learning to say, oh, not only can I take action AJ to communicate goal G, I can take action AI, and the receiver updates its learning to say, oh, not only when I see action AI does that mean goal G, when I see action AJ, that means goal G. So this is how this kind of equivalence class ends up emerging through this process. Okay, so now let's talk about empirical results. So the left picture is, a little bit different. So the left picture is still the same, or this is still the same game, the same discrete domain that I showed you earlier. But now what we see is when we use quasi-equivalence discovery, the agents are able to learn equivalence classes. They're actually able to learn that like all of the actions 1 through 4 belong to the same equivalence class. So and all the actions 5 through 8 belong to the same equivalence class. So now the sender learns that when it takes, when it's trying to communicate goal G, it should still only take action 0. That's still the same. But when it tries to communicate goal 1, there's an equal probability distribution over any of the actions 1 through 4 that it can take, and so on and so forth for the other goals. And the receiver learns if I see actions, any of the actions 1 through 4, it still means intent 1. So now the nice thing about this is there's only one way to optimally map goals, communicative goals, to equivalence classes over actions. So here's the baseline using self-play on the left side. You don't need to see all of the different, you don't need to see everything. What I really want to draw your attention to is the fact that these are 5 different joint policies that are all equivalent but incompatible. They all take action 0 for goal 0, but they permute actions 1 through 4 for goals 1 through 4. Whereas when we use QED to train, now what you see is there's really only one way to map goals to equivalence classes over actions. So effectively, all of the joint policies on the right side are learning the same communication protocol. And if you look at performance-wise, they perform similarly with respect to self-play, but with respect to zero-shot coordination and cross-play, there's a huge difference in terms of how self-play agents are able to do with new partners and the QED agents are able to do with new partners. And it's because effectively they learn the same communication protocol on the right side. There is the trade-off of energy, however. If you look at the sender policies on the right side, so like the left column, but on the right side, the probability mass is over the entire action space, which means it's also over more costly actions. Versus on the left side for self-play, the probability mass is only on like the first 5 actions. So it's a more costly communication protocol from the perspective that that all of the actions get used, but it engenders much greater zero-shot communication success. So we increase communication performance with novel agents by about 60%. So,
Kalesha, you have 5 more minutes.
Okay, thank you, Ruth. Okay, so I'm actually about to wrap up soon. So I want to show one open challenge, which is the prevalence of suboptimal protocols. So, so it is the case that, when we can get a communication protocol that looks like this is optimal, and this is ideally what we want to see. And one way to interpret that is for each intent, like, so the intents are ranked 0, 1, 2, 3, 4. The energy exertion, so for intent 0, the energy exertion of the action is mapped to is energy of 0. For intent 1, the energy exertion of the actions there, it's mapped to our energy class 1. Intent 2, energy exertion, energy class 2. So there's this kind of direct, mapping of the indices. What we also saw is that there are many suboptimal protocols. So it is the case that maybe only 10 to 20% of the time, on average, are we actually seeing the agents that converge on the optimal protocol. So there's the prevalence of converging on suboptimal protocols. That's still a challenge. And I mean, this is a greater challenge in deep learning more generally, where you have lots of optima. And so it is the case that your optimization algorithm, given that it's a local, like a gradient-based optimization algorithm, is likely to converge on, on different runs of the method. It can converge on suboptimal solutions. But I did want to show that, like, this is one challenge that is pretty important, I think, is trying to figure out how to more robustly converge on optimal. When it converges on optimal protocols, it works really well for zero-shot communication, but it's dependent upon converging upon some optimal protocols. So on the right side, we see 3 different examples of suboptimal protocols, and basically what it does is permute the energy classes. So for example, if you look at the very top one, intent 0 is still mapped to action 0, to an action that exerts energy 0, but intent 1 is mapped to actions that exert energy of 3. Or like intent 2 is mapped to actions that exert energy class of 1. So we see that it basically permutes these energy classes. Okay, so a recap of the zero-shot communication work. So the motivating goal is the emergence of communication protocols that generalize to novel partners. And the key novel challenges that we explored are looking at costly channels, which we are assuming are deriving from energy exertion, but it could derive from other sources of cost, and high dimensional continuous channels motivated by embodied agents, which I didn't talk about in this talk. I do have hidden slides on it, so if somebody's interested later, I'm happy to talk more about that. But I wanted to kind of delve more into the foundational questions and the theoretical analysis, so I focused only on costly channels in this talk. And the key contributions of that work is that we formally introduced a zero-shot communication problem setting. We incorporated realistic priors and cost constraints to induce learning bias, theoretical analysis of the communication objective with equivalence classes, and then the QED method for inferring and generalizing over these equivalence classes. And some of the open challenges here that I think are really important is some theoretical analysis of sample complexity of the QED algorithm, because this inner loop does have to learn lots of joint policies or communication protocols. And then guiding the policy search to more robustly converge on a global optimum. So I showed you what suboptimal solutions look like. With respect to learning human compatible protocols, which I didn't touch, I think that because these communication protocols are still very much in this space of the protocol itself is not semantically meaningful. And so, if you have agents that are communicating with humans, then we want a semantically meaningful communication. So we want it to be the case that agents learn communication protocols that are compatible with each other, but we also want to be the case they're compatible with humans. And so then I think you can introduce something like supervisory signal or data or other kinds of realistic priors that humans might use in order to make it the protocols more semantically meaningful. And then something I am more interested in these days is thinking about mixed motive settings. Social dilemmas in particular, where you have agents where what we want to see is cooperation, but agents may have some degree of self-interest. And so then this really takes you from a setting of like thinking about communication protocols, so information exchange for efficient coordination, to negotiation protocols aligning incentives to enable cooperation. So in the case where you have some self-interest, you can't assume that agents are fully cooperative, and therefore you can't necessarily assume that you want to yet solve the coordination problem until you figure out how to get agents to align their incentives. So negotiation could be one way to do this, and thinking about negotiation protocols that could generalize to partners that you haven't seen could be an interesting challenge. Okay. And so, yeah, that's it. I don't have a thank you slide, but if I did, it would say thank you, and that's the end.
Thank you very much, Kalesha. That was fascinating talk. We have a couple of minutes for questions if anyone wants to join in, maybe Ignacio or Elliot at Vienna if someone has a question there.
Yeah, it's on mute. I don't know if anyone has a question. You can come here and ask her or raise your hands. I don't know. Yeah, you want to join in? That's gonna be easier probably. Yeah, someone here has a question. They're about to ask. Yeah, Kalesha, thanks so much for the talk. It was great. One thing I think is really cool about the algorithm is that you're able to compute the symmetries in the problem in this like lazy iterative way. So my main question was just if you've thought about ways for like pre-computing these symmetries before having to solve for these optimal policies, so that you can like already pre-compute some of the symmetries before having to do this iterative search process, maybe helping with the conversion guarantees or something like that.
Yeah, that's a good question. I haven't thought about that. That's not something that we thought about, but I could imagine that you have some kind of a policy that like explores in the environment, so more like kind of the single agent RL regime, and tries to, because I mean the symmetries, what they try to capture is grounding in the environment. So the idea of energy is physics. I mean, so it's effectively saying, you know, there's some actions that require more energy from me, and therefore I should, you know, think about those as more costly. But you could imagine if there were a robot arm in an environment, it could like explore different actions it could take in this environment and try to discover what actions are more costly without having to actually do that through the interaction. And then the interaction kind of exploration in the communication learning could just be more about how to map the actions to goals. I mean, to be fair, in this discrete setting, we did already assume that the actions have energies that they are given, and that as the agents get reward for a communication protocol, they would learn that they would figure out how to minimize that, but they didn't explicitly have to figure out the mapping between the actions and the ways in which they're grounded to energy. But in the continuous setting, this was really a challenge trying to like effectively couple those problems because you have motion trajectories and there are many more motion trajectories that can belong to an equivalence class. So thinking about like decoupling those problems by doing some exploration in the environment first could be a really interesting, promising avenue, I think.
Thanks, Kalesha.
Any additional questions there?
I don't know if any of the guys, doesn't seem here. Anyone online?
Stefano made a comment earlier. Stefano, maybe you want to say something? Okay, so one thing that I wanted to say, if yeah, he's not here at the moment. Our theme today basically is about benchmarking for ad hoc teamwork, and it seems like the work that you've been doing so far is a fantastic part or component of an algorithm and an approach that we would like to use as a benchmark and to compare against. What would you think you can add on this work or make it more benchmarkable so it will be easy to use and to compare, or what's important to extend here?
Yeah, no, that's a good question. I think, so one thing that we, you know, struggled a bit with and went back and forth with is like domains. I think like finding a good domain, like, so, and particularly in the continuous work, I know I didn't get a chance to talk about that because I dived into the, you know, kind of the analysis for the discrete domain, but it's really, I mean, I think you need meaningful domains where the communication will help coordination, and you also having more general communication helps, you know, some overall set of goals in the environment. I mean, you know, like I think like, for example, autonomous driving is a nice general domain to motivate because you wouldn't want, you know, if cars had to communicate with each other with other cars later, you wouldn't want to be the case that every single time they have to learn a new protocol, right? But then how do you take something like that and actually make it a benchmarkable domain that you can test on? I think that would be really nice. Or like for the continuous domains, you would need something with trajectory like skill learning, perhaps, and the communication skills themselves are in the context of maybe some other kinds of skills that maybe like a robot might learn or something like, but something, I think domains are a key part of like making this such that you can benchmark it, you can test different methods, you can see like why like in some broader context. I think the theoretical question seems intuitive, like that you would want communication protocols that are general. So I think people understand that, and that's been nice, but it would be nice to have like domains that actually make it quite clear why this is quite compelling to have. And this is how different methods compare when they try to do this, or different models compare, or, you know.
Yeah, so we started working on that in Stefano's group and myself on what are the attributes that you want in a domain that would be interesting. And I was thinking maybe symmetries sound like something like that you can maybe rank different domains according to how easy it is to elicit symmetries from. That might be something that's worth investigating. Definitely.
Yeah, I think so. Because I think symmetries, this idea, I mean, because symmetries just is another word for equivalences, right? And I think that pops up a lot. I mean, I talked about action symmetry, which is really about two different ways to communicate the same thing, but there's also goal symmetry, which we didn't touch, which is also an interesting question, which is really about the same action communicating different things, right? Like when I do some gesture or I say something, it can mean different things. And that's another kind of symmetry that's really important in. And from a coordination perspective, I think part of what makes humans interesting is that we can adapt to expressivity and ambiguity quite well. But I think that's what the action symmetry tries to capture expressivity, many different ways to say the same thing, and goal symmetry captures ambiguity, the same action being interpreted different ways. And I think humans are really good at being able to like navigate these kinds of things, but I think they occur naturally a lot. And so AI agents that need to be able to interact with human agents, I think it's important, like symmetries represents an important part of the, you know, space that for exploration. Yeah.